Chapter 19. Rivers and Floods. Water covers such a large proportion of the earth's surface, and is such an important factor in the economy of nature, that it becomes a matter of interest to study the process of its distribution. Water is to our globe what blood is to our bodies. A constant circulation must be kept up, or all animal and vegetable life would suffer. Here, as in every other operation of nature, the sun is the great heart and motive power that is active in the distribution of moisture over the face of the globe. The total annual rainfall on the whole surface of the earth amounts to about 28,000 cubic miles of water. Only about 1/4 of this amount ever reaches the ocean, but it is either absorbed for a time by animal and vegetable life, or lifted through the process of evaporation into the air as invisible moisture, when it is carried over the region of rainfall and there condensed into water and falls back upon the earth, only to go through the same operation again. The whole surface of the earth is divided into drainage areas that lead either directly through rivulets and rivers to the ocean, or into some landlocked basin, where it either finds an outlet underground or is kept within bounds through the process of evaporation, the same as is the case with our great oceans. In North America the amount of drainage area that has no outlet to the ocean amounts to about 3% of the whole surface. In other countries the percentage of inland drainage is much larger. The Great Salt Lake in Utah is an instance where there is no outlet for the water except through the medium of evaporation. Inasmuch as all rivers and streams contain a certain proportion of salt, especially in such strongly alkaline land regions as the Great Basin of the North American continent, these inland lakes in time become saturated with this and other mineral substances. Salt is constantly being carried into the lake by the water of the stream that feeds it, and the water is continually being evaporated, leaving the salt behind. This process has been going on in the valley of Utah for so long a period that 17% of the contents of the lake is salt. The Humboldt River in Nevada, which empties into a small lake of the same name and lies at the foot of the Humboldt Mountains, is said to have an underground outlet. This must be the case, because the area of the lake is very small as compared with Salt Lake, while the river that feeds the latter is very small compared with the one that flows into the former. That is to say, in the one case a very small stream empties into a large lake, while in the other case a much larger stream feeds a very small lake. Besides, Humboldt Lake, unlike the Great Salt Lake, is said to be a freshwater lake. If it had no outlet it would become in time saturated with salt. The largest body of water in the world having no outlet to the ocean is the Caspian Sea, on the border between Asia and Russia in Europe, it being 180,000 square miles in extent. Where rivers empty into large bodies of water, such as the great chain of lakes on the northern border of the United States, and these lakes have an outlet connecting one with the other, and finally by a river to the ocean, a constant circulation is being kept up, and the water remains fresh. Owing to the fact, however, of the great evaporating surface that these lakes afford, there is a greater disproportion between the rainfall upon the drainage area tributary to these lakes, and the amount of discharge through the St. Lawrence River, than would be the case with a river that was not connected with a system of lakes. The amount of rainfall upon the area drained by the Mississippi River during one year amounts to about 614 cubic miles of water, while the discharge at the mouth of the Mississippi River is only about 154 cubic miles. The difference between the two figures has been carried up by the process of evaporation or stored in vegetation. These figures vary considerably, however, with different years. The proportion of rainfall to discharge will vary greatly in different rivers from other causes than having a large evaporating surface. This variation is due to the difference in the ability of the soil to retain water after a rainfall. In some drainage areas the ground is more or less impermeable to water, and in this case the water runs readily off, causing a sudden rise in the river, and as suddenly it reaches the low water mark. In other drainage areas the ground is very permeable to water, so that the rain penetrates to a greater depth into the earth, where it is held, and by a slow process drains into the rivers, while much more of it is carried off by evaporation, and into vegetation, than is the case in the drainage district before mentioned. The courses of rivers are determined by the topography of the country through which they follow. The sinuous windings, that are found to be a characteristic of nearly all rivers, are caused by the water, through the force of gravity, seeking the lowest level and avoiding obstructions, which they can flow around more easily than remove. Great rivers often change their courses, especially where they flow through a region of made earth, such as is the case with the lower Mississippi River, and in other great rivers of the world. The loose earth is continually shifted by the current, and where the current is not very strong it will often hold the water back to such an extent of accumulated weight that the flood will break over at some weak point on its banks and make a new course for itself. One of the great rivers of China, the Huanghe, often causes dire destruction to life and property owing to change in its bed from time to time. It is estimated that between the years of 1851 to 66, this river caused the loss of from 30 million to 40 million lives through drowning and famine by the destruction of crops. Floods in rivers are occasioned from various causes. Of course the primary cause is the same in all cases, that is, from precipitation of moisture in the form of rain or snow. Some rivers are so related to the area of rainfall and to the permeability of the soil that there is but little variation in the amount of discharge throughout the year. The great river of South America, the Amazon, is an instance of a river of this class. A certain number of the small rivers that feed it lie in the area of rainfall during the whole of the year. For instance, the streams of the upper Amazon are being fed by rains at one season of the year, when those feeding the river lower down are at the lowest stage. When the rainy season prevails in the upper section of the river, the dry season prevails farther down, while at another season of the year these conditions are reversed. Therefore, though the Amazon has a larger drainage basin than any other river in the world, and in some parts the yearly rainfall is 280 inches, there is no very great fluctuation in the stages of water. The Orinoco River, which flows through Venezuela, and whose drainage area is largely covered with mountains, has a greater fluctuation than any other river, the difference between high and low water amounting to 70 feet. The river Nile has an annual rise of from 14 to 26 feet. This river is the sole dependence of the inhabitants of Lower Egypt, and their sustenance depends upon the height to which the river rises. If it does not rise high enough, the agricultural lands are not sufficiently irrigated, and if it rises too high, their crops are destroyed by the floods. In this section they depend entirely upon the overflow of the Nile for irrigation, and not upon the rainfall. There is scarcely ever a rainfall in Lower Egypt except about once a year on the coast of the Mediterranean. After ascending the river for a short distance, we come into an area of no rain for a distance of 1,500 miles along the river. Egypt has a superficial area of about 115,200 square miles, and only about 1/12 of this area is in a position to be cultivated. As there is no rainfall in this region, the sole dependence for agricultural purposes is from the river Nile, when it rises to a sufficient height to admit of irrigation. The river brings down quantities of rich earth, which during the overflow is deposited, and thus the agricultural regions are refertilized annually. The river Nile is what is called a tropical river, and is fed by the rains in Upper Egypt caused by the monsoon winds that prevail in that section of Africa during the summer season, as they do in India. As has been explained in a former chapter, the monsoon winds blow steadily for about 6 months from off the Southern Ocean. These winds are highly charged with moisture, which is not precipitated till it strikes the mountainous regions of the interior. Here the high mountains, which are often snow-capped, cause a profuse precipitation, which runs off into the various feeders of the Nile, causing a gradual rise in the river that reaches the highest point about September of each year. If the Nile should dry up, or if the annual flood should materially change in height, it would make a desert region of all that portion of Egypt now so productive. The great rivers of China, the Yangtze Kiang and the Huanghe, are also tropical rivers and have an annual flood. Sometimes the rise is as much as 56 feet. These annual floods are also caused by the monsoon winds that carry moisture from the ocean, which is condensed and precipitated in the mountains of Central Asia. The conditions are substantially the same as those which prevail at the sources of the Nile in Africa. Rivers are produced from all sorts of causes, some of them flowing only during the rainy season, while others are fed by melting snow from the higher mountains, and as the snow is rarely melted away entirely during the summer in the high mountains, there is a continual flow from this source. The snow forms a system of storage, so that the water is held back and is gradually given up as it melts. If this were not true, mountainous regions would be subjected to disastrous floods. If the precipitation were always in the form of rain, it would immediately run off instead of being distributed over a whole system. The Platte is an instance of a river largely fed by the melting snows of the Rocky Mountains. In the region of glaciers in the mountains of Alaska and Switzerland, rivers are fed by the melting ice. These rivers are usually of a milky color occasioned by the pulverization of rock caused by the grinding of the great glaciers as they flow down the gulches in the mountain side. In some regions these glacial rivers have a diurnal variation. This is caused by the fact that the glacier is so situated that it freezes at night, which checks the flow, and thaws in the daytime, which increases it. Rivers are to the globe what the veins are to the animal organization. They pick up the surplus moisture not needed in the growth of vegetation, and for the sustenance of animal life, and carry it on, together with the debris that it gathers in its course, to the great reservoirs, the seas and oceans, where it is distilled and purified by the action of the sun's rays. From here it is carried back in the form of invisible moisture, and again precipitated in the purified state, to help carry on the great operations of growth, animal and vegetable. The vaporized moisture that is carried back by the winds and redistributed corresponds to the blood, after it has been purified, and is carried back through the arteries to the extremities and capillary vessels which feed and nourish the bodily organs. Chapter 20. Tides. Anyone who has spent a summer at the seashore has observed that the water level of the ocean changes twice in about 24 hours, or perhaps it would be a better statement to say that it is continually changing, and that twice in 24 hours there is a point when it reaches its highest level and another when it reaches its lowest. It swings back and forth like a pendulum, making a complete oscillation once in 12 hours. When we come to study this phenomenon closely we find that it varies each day, and that for a certain period of time the water will reach a higher level each succeeding day until it culminates in a maximum height, when it begins to gradually diminish from day to day until it has reached a minimum. Here it turns and goes over the same round again. It will be further observed that the time occupied between one high tide and the next one is a trifle over 12 hours. That is to say, the two ebbs and flows that occur each day require a little more than 24 hours, so that the tidal day is a little longer than the solar day. It corresponds to what we call the lunar day. As all know, the moon goes through all its phases once in 28 days. The tide considered in its simplest aspect is a struggle on the part of the water to follow the moon. There is a mutual attraction of gravitation between the earth and the moon. Because the water of the earth is mobile, it tends to pile up at a point nearest the moon. But the earth as a whole also moves towards the moon, and more than the water does, keeping its round shape, while its movable water, practically enveloping it, is piled up before it toward the moon and left accumulated behind it away from the moon. So that in a rough way it is a solid sound earth, surrounded by an oval body of water, the long axis of the oval representing the high tides, which, as they follow the moon, slide completely around the earth once in every 24 hours. Thus there are really two high tides and two low tides moving around the earth at the same time, and this accounts for the two daily tides. We have accounted for the time when they occur in the fact that the water attempts to follow the moon, but this does not account for the gradual changes in the amount of fluctuation from day to day. The problem is complicated by the fact that the sun also has an attraction for the earth as well as the moon, but from the fact that the sun is something like 400 times further from the earth than the moon is, and also the fact that the attraction of one body for another varies inversely as the square of the distance, the moon has an immense advantage over the sun, although so much smaller. If the power of the moon were entirely suspended, or if the moon were blotted out of existence, there would still be a tide. The fluctuation between high and low tide would not be nearly so great as it is at present, but it would occur at the same time each day, because it would be wholly a product of the sun. It will be easily seen that these two forces acting upon the water at the same time will cause a complicated condition in the movement of the waters of the ocean. There will come a time once in 28 days when the sun and the moon will act conjointly, and both will pull in the same direction at the same time upon the water. This joint action of the sun and moon produces the highest tide, which is called the spring tide. From this point, however, the tides will grow less each day, because the relation of the sun and moon is constantly changing, owing to the fact that it requires 365 days for the sun to complete his apparent revolution around the earth, while the moon does her actual course in 28 days. When the sun and moon have changed their relative positions so that they are at right angles to each other with reference to the earth, at a quarter circle apart, the sun and moon will be pulling against each other, At least this is the point where the moon is at the greatest disadvantage with reference to its ability to attract the water. Because one quarter around the earth the sun is creating his own tide, which to that extent counteracts the effect produced by the moon, the tide under the moon at this point is at its lowest point, and is called the neap tide. When the moon has passed on around the earth to a point where it is opposite to that of the sun, at a half circle apart, there will be another spring tide, and then another neap tide when it is on the last quarter, and from that point the tide will increase daily until it reaches the point where the sun and moon are in an exact line with reference to the earth's center, when another spring tide occurs. From this it will be seen that there are 2 spring tides and 2 neap tides in each 28 days. This is the fundamental law governing tides. There are many other conditions that modify tidal effects. Neither the sun nor the moon is always at the same distance from the earth, so that there will be a variation at times in high and low tides. For instance, it will happen sometimes that when both the sun and moon are acting conjointly, they will both be at their nearest point to the earth, and when this is the case the spring tide will be much higher than usual. For many years the writer has observed that artesian wells, made by deep borings of small diameter into the earth to a water supply, have a daily period of ebb and flow, as well as a neap and spring tide, the same as the tides of the ocean, except that the process is reversed. The time of greatest flow of an artesian well will occur at low tide in the ocean. This might be accounted for from the fact that when the tide is at its height, the moon is also pulling upon the crust of the earth, which would tend to take the pressure off the sand rock which lies 1,000 or 2,000 feet below the surface, and through which the flow of water comes, and thus slacken the flow. When the moon is in position for low tide, the crust of the earth would settle back, and thus produce a greater pressure upon the water-bearing rock. This is the only theory that has suggested itself to the writer that would seem to account for these phenomena. Looked at from one standpoint, it is easy to account for tidal action, but when we attempt to make up a table giving the hour and minute as well as the height of the tide at that particular time, we find that we have a very complicated mathematical problem. However, tables are made out so that we know at just what time in the day a tide will occur every day in the year.
Chapter 21. What is a Sponge? Before entering upon the great subject of water and ice, 2 of the most tremendous factors in world-building, let us consider a small matter, so far as its permanent effects are concerned, yet one which enters largely into the comfort and health of mankind, and which, though an animal, may be discussed where it belongs, under water. There are few things more familiar about the ordinary household than a piece of sponge, and yet, perhaps, there are but few things about which there is so little known. The sponge had been in use many, many years before it was given a place in either the animal or vegetable kingdom. The casual observer, because he saw it attached to a rock, jumped to the conclusion that it was of vegetable origin. But after being kicked back and forth, so to speak, from one kingdom to the other, even by what are called well-educated people, it has finally been received into the family of animals, a dignity in which the sponge itself seems to take but little interest. The sponge is found in the bottom of the sea, at no very great depth however. It is usually attached to a rock or some other substance, and it is due to this fact chiefly that it has been classed as a vegetable. At least one scientist has attempted to give it a place between the 2 kingdoms, but this only adds confusion without giving any satisfactory explanation of its origin. It seems to belong to a very low order of animal life. It breathes water instead of air, but probably, like many other water animals, it absorbs the oxygen from the air which is more or less contained in the water. There is a process of oxidation going on within the sponge, in a manner somewhat as we find it in ordinary animal life, and like the animal it expels carbon dioxide. All this, however, is carried on apparently without any lungs or any digestive organs, or, in fact, any of the organs that are common to the animals of the higher order. The sponge, however, as we see it in our bathrooms, is only the framework, bony structure, or skeleton of the animal. the sponge is exceedingly porous and readily absorbs water or any fluid by the well known process of capillary attraction. The sponge fiber is very tough and is not like anything known to exist in the vegetable kingdom. The substance analyzes almost the same as ordinary silk, which all know is an animal product. If we burn a piece of sponge, it exhibits very much the same phenomena as the burning of hair or wool, and the smell is very much the same. The structure of a piece of sponge, when examined under a microscope, is a wonderfully complicated fabric. Under the microscope it shows a network of interlacing filaments running in every direction in a system of curved lines intersecting and interlacing with each other in a manner to leave capillary openings. It is a wonderful structure, and one that a mechanical engineer could get many valuable lessons from. It will stand a strain in one direction as well as another. There are no special laminations or lines of cleavage. It is very resilient or elastic, and readily yields to pressure, but as readily comes back to its normal position when the pressure is relieved. If we examine the body of a sponge, we shall notice that there are occasional large openings into it, but everywhere surrounded by smaller ones. If we should capture a live sponge and place it in an aquarium with sea water, where we could study it, we should find a circulation constantly going on, and that water was constantly sucked in at the smaller openings all over the outside of the sponge, and as continuously ejected from the large openings. This process constitutes what corresponds in the higher order of animals to both respiration and blood circulation combined. The sponge feeds upon substances that are gathered up from the sea water, and breathes the air contained in the same, so that it breathes, eats, and drinks through the same set of organs. When we first capture a live sponge from the sea, it has a slimy, dirty appearance, and is very heavy. The sponge is found to be filled with a glutinous substance that is the fleshy part of the animal. It is very soft and jelly-like, and after the sponge is dead, it is readily squeezed out by a process which is called taking the milk out, which leaves simply the skeleton, the only useful part as an article of commerce. This fleshy substance, in life, has somewhat the appearance and composition of the white of an egg. The mechanical process by which the sponge takes its nourishment is exceedingly interesting. There are small globe-shaped cells with openings through them that are lined with little hair-like projections that move in such a manner as to suck the water in at one side of the cell and push it out at the other. These little fibers are technically called cilia. We might describe them as little suction pumps that are located at many points in the sponge, all acting conjointly to produce a circulation through the finer openings, or capillary vessels, and finally discharging into the larger chambers which carry off the residue. If we should analyze the water as it is sucked into the sponge, and that which issues from it through the larger openings, we should find a difference between the two. The expelled water would contain more or less carbon dioxide. There are many different varieties of sponge, and while they all possess certain characteristics in common, they are still very different in many respects. Some of them are large and coarse, while others are exceedingly soft and velvety. What is called a single sponge is a colony of animals rather than a single animal. At least they are so regarded by zoologists. This can hardly be true if we regard the sponge itself as a part of the animal. If the sponge is simply regarded as the house in which the animal lives, then it becomes a great tenement with numerous occupants. But it is a tenement upon which the life of the sponge depends, and is a part of it. The sponge could not breathe without the fibrous structure in the cells containing the machinery for producing the circulation. It will be seen that the sponge, while it is an animal, is of the very simplest variety, so far as its organs are concerned. True, its framework is very complicated, but the organs for sustaining the life of the animal are the simplest possible. The little self-acting pumps pull the water into the sponge through the smaller openings, where it appropriates the food substance from the water, and where a chemical action takes place which builds up the fleshy substance of the animal, and then expels the residue which is not needed to support its life. Simple as it is, however, as a mechanical structure, the life and growth of the sponge is as mysterious as that of the most highly organized animal, or even the soul of man. We can study out the structure of a plant or animal. We can analyze it and tell what are the elements of which it is composed. We can describe the mechanical operations that are carried on, and the chemical combinations that take place, but no man has ever yet solved the mystery of life, even in the lowest form, whether animal or vegetable. The sponge, whether considered as a single or compound animal, has the power to reproduce itself, and here the mystery of life is as much hidden as it is in God's highest creation. It has been stated that every sponge contains a large number of separate cells which carry on the operation of circulation and respiration, and may be likened to the heart and lungs of an animal of a higher creation. Zoologists claim that each one of these cells represents a separate animal, living in a common structure. However this may be, it is an interesting fact that the sponge has the power of secreting ova that grow in large numbers in little sacs until they have reached a certain stage of progress, when they are expelled from the mother sponge and turned adrift in the great ocean to struggle for their own existence. These eggs do not differ much in their structure and composition from an ordinary hen's egg, except that there is no shell, only a skin provided with little fibers, called cilia, that project from it, and by the movement of these the embryo sponge is able to propel itself through the water. It thus lives until it has reached a certain stage of development, when it seeks out a pebble or rock to which it attaches itself at one end, preparation for which has been made by its peculiar structure during its life, when it was free to float around through the water. It is now a prisoner, and chained to the rock it has selected for the foundation of its home. Having no longer any use for the little cilia which enabled it to swim through the water, it now loses them. Here is a beautiful illustration of how nature provides for the necessities of the smallest things, and how, when the necessity that demanded a certain condition passes by, the condition passes with it. The embryo begins to show a fibrous development, which is the beginning of the framework of a new sponge. Evolution goes on, every step of which is as mysterious as a miracle, until the growing thing is a full-grown sponge, equipped with the means for respiration, circulation, feeding, digestion, and reproduction. Sponges grow in the bottom of the sea at different depths. They are obtained by divers who make a business of gathering them. The best sponges are called the Turkish sponge, which are very soft and velvety, and may be bleached until they are nearly white by subjecting them to the action of certain acids. The divers become very expert, but they do not have the modern equipments of a diving suit. The Syrian divers in the Mediterranean go down naked with a rope attached to their waists and a stone attached to the rope to cause them to sink, together with a bag for carrying the sponges. They have trained themselves until they can remain under water from a minute to a minute and a half, and in that time can gather from 1 to 3 dozen sponges. The ordinary depth to which they descend is from 8 to 12 fathoms. But a very expert diver will go down as far as 40 fathoms. The better class of sponges are said to grow in the deeper waters. The coarse, inferior sponges are called the Bahama sponge. This sponge is of a peculiar shape, growing more like a brush, with long bristly fibre. The trade in sponges is quite large. The consumption in Great Britain alone amounts to about $1,000,000 per annum. The sponge as an animal possesses many advantages over his more aristocratic neighbour, man. He breathes, but he has no lungs, and therefore cannot have pneumonia. He digests his food, but he has no stomach, and therefore never has dyspepsia, gastritis, or any of the many ailments that belong to that much abused organ. He has no intestines, and therefore cannot have appendicitis or Asiatic cholera, or any of the long train of diseases incident to those complicated organs. He has no nervous system. O happy sponge! Therefore he cannot have nervous prostration, hysteria, or epilepsy. He has no use for doctors, and therefore has no unpleasant discussions with his neighbours about the relative merits of the different schools of medicine. If he has any predilections in the way of pathies, we should say that he is a hydropath. While he is a great drinker, he is not at all convivial. He drinks only water, and takes that in solitary silence. He sows all his wild oats when he is very young, while he has the freedom to roam at will. He soon tires of this, however, for he selects the rock that is to be the foundation of his future home, and there settles down for life, wrapped in the solitude of his own originality. He is not troubled with wars or rumours of wars. His eyes are never startled, or his nerves shaken, by the scare headlines of yellow journalism. The one sensation of his life, if sensation he ever has, is when a great ugly creature of some oriental clime comes down to his home and tears him away from his native rock, carries him to the surface, and there literally squeezes the life out of him. He finally dies of the grip, and here he sinks to the level of his more aristocratic neighbour. But there is another side to our philosophy. If the sponge is exempt from all these ills that we have enumerated, it is because he is incapable of suffering, and is therefore incapable of enjoyment. Those beings that have the ability to suffer most have also the ability to enjoy most. The higher the type of civilization, the greater possibilities it offers for real enjoyment, also for real misery. This being true, it should be the aim of highly civilized people to eliminate, as far as possible, those things that make for misery, and cultivate those things that make for happiness in the highest and best sense.
Chapter 22. Water and Ice. We now have entered upon a subject that is of intense interest, studied from the standpoint of facts as they exist today, and of history as we read it in the rocks and boulders that we find distributed over the face of the earth. The whole northern part of the United States, extending to a point south of Cincinnati, was at one time covered with a great ice sheet, traces of which are plainly visible to anyone who has made anything of a study of this subject. The glaciers now to be seen in British Columbia and Alaska, great as they seem to one viewing them today, are by comparison with what once existed simply microscopic specks of ice. Glaciers, like rivers, flow by gravity, following the lowest bed and lines of least resistance. The difference being that in the one case the flow is rapid, while in the other it is scarcely visible, except by measurement from day to day. Before entering upon a description of the law that governs the flow of glaciers, let us stop and give a little study to the phenomena of water as exhibited when it is at the freezing point. Water is such a large factor in the makeup of our globe and the air that surrounds it that it becomes a very interesting and important study to anyone who wishes to understand the phenomena of nature that are closely related to it. As all know, pure water is a compound of two gases, oxygen and hydrogen, combined in the proportion of 2 atoms of hydrogen and 1 of oxygen. Let us now study this fluid in its relation to heat. The reader is referred to the chapters on heat in Volume 2, where it is stated that heat is a mode of motion. It is also stated that heat is a form of energy, and that energy is indestructible, that an unvarying amount of it exists in some form or another throughout the universe. It is not always manifested as heat or electricity, although both of these are always in evidence as active agents of force. Much of the energy is simply stored, all the time possessing the ability to do work or to be converted into any of its known forms, such as heat, light, electricity, or mechanical motion. A weight that is wound up has required a certain amount of energy to elevate it to the position that it occupies. While in its elevated position, it possesses energy, although not active. Energy in this form is called potential energy, or possible energy, and has the power to do work if released. Active energy is also called kinetic energy, or moving energy, and the sum of these two energies is a constant quantity. We will now study energy as it is related to water in the form of heat. There is a kind of heat called latent heat, which is not heat at all, but stored energy, waiting to be turned into heat or light or some other active form. Properly speaking, heat is a movement of the atoms of matter, the intensity of which is measurable in degrees and called its temperature. To use the term latent heat as meaning concealed heat, which must reappear as heat, is a misnomer and is very misleading. If it is proper to call a wound-up spring or weight latent heat, then its present use is a correct one. What was formerly termed latent heat is simply a form of potential energy. When sensible heat that is measurable as temperature disappears in the performance of some sort of work, especially in connection with certain phenomena relating to water, we call it, or rather miscall it, latent heat. But the phrase would better be stored energy. The action of water under heat is very peculiar, and in order to get a correct understanding of the phenomena exhibited in glacial action, we also need to understand the phenomena of water at the freezing point. As is well known, fresh water freezes at 32 degrees Fahrenheit, and at the moment of freezing there is a sudden expansion to such an extent that a cubic foot of ice will occupy a much larger space than it will in the form of water. And because it occupies so much larger space, it is lighter than the same bulk of water would be, and therefore it floats in water. At the point of freezing, the thermometer, if placed on the ice, will register 32 degrees. If the ice is allowed to melt, the water at the moment of liquefaction would be found to register the same degree of temperature as the ice when first frozen. And yet there has been a vast expenditure of energy between the points of liquefaction and congelation, notwithstanding the temperature of ice may be lowered, after it is formed, many degrees, which is measurable by the thermometer. Suppose we take a piece of ice which is 10 degrees below the freezing point, and insert in it a thermometer. If now we apply heat to this ice, the thermometer will gradually rise until it reaches the melting point at 32 degrees Fahrenheit, where it will stand until all the ice is melted. The application of heat is going on steadily, but there are no indications of movement in the mercury until the last trace of ice with which it is in contact has been liquefied. After the ice is all melted, if the application of heat to the body of liquefied ice be continued, the column of mercury will rise its movement upward until it reaches the boiling point, where it is again arrested. At no matter how much heat is applied to the boiling water, if in an open vessel, the thermometer remains the same until all the water is evaporated. Here are two curious facts, and they are facts that, if we can master them, will serve as a key to the understanding of much that is mysterious in nature. It will be our endeavor to give the reader a mental picture of what is taking place during the time the ice is melting and the thermometer is stationary. Do not suppose that you can understand this, even so far as it is understandable, by a casual reading without thought. No man was ever yet able to present a picture to the mind of another, however clearly and simply it may be done, unless that other mind is receptive. When a photographer trains his camera upon an object, however intense the light may be, and however clean-cut the picture that is thrown upon the plate in the camera, unless that plate is properly sensitized so that the picture may be impressed upon it, all of the other conditions are in vain. The reader is always a part of the book he is reading.
Chapter 23, Stored Energy in Water. In our last chapter we traced the upward movement in the mercury of the thermometer from 10 degrees below the freezing point up to the boiling point of water. we found that the thermometer was arrested at 32 degrees and remained stationary at that point until all the ice was melted, notwithstanding the fact that heat was being constantly applied. After the ice is all melted, the mercury moves upward until it reaches the boiling point of water, where the movement is again arrested, and although the heat is being continuously applied, it remains stationary until all the water is evaporated. If we push the process still further with a sufficient application of energy, we can separate the vapor molecules into their original elements, oxygen and hydrogen. Let us go back now to the freezing point of water and see what is becoming of the heat that is consumed in melting the cake of ice, and still does not produce any effect upon the mercury in the thermometer. Sensible heat, as before stated, is a movement of the atoms of matter, and temperature, as it affects the thermometer, is a measure of the intensity of motion exhibited by these atoms. In the experiment of the block of ice that in the beginning is 10 degrees below the freezing point, as shown by the thermometer, the molecules have a definite intensity of motion. The intensity of this motion increases when heat is applied until it reaches 32 degrees, when it remains stationary until all of the ice is melted. At this point there is a rearrangement of the molecules of water as it assumes the liquid state. To perform this rearrangement requires a certain amount of work done, which is analogous to the winding up of a weight to a certain distance. There has been energy used in the winding up of the weight, but that energy now is not destroyed, nor still in the form of heat, but is in the potential state, ready to do some other kind of work. So the heat that has been applied to the melting ice has been utilized during the process of its liquefaction in rearranging the water molecules and putting them in a state of strain, so to speak, like the weight that is wound up to a certain height. There is a certain amount of potential energy that is stored in the molecules of water that will be given up and become active energy in the form of heat if the water is again frozen. To melt a cubic foot of ice requires as much heat as it would to raise a cubic foot of water 144 degrees Fahrenheit. But as we have seen, while all of this energy is absorbed as heat, it is not lost as energy. It ceases to be kinetic or active and becomes potential energy. This, let us repeat, has been called latent heat. The term grew out of the old idea that heat was a fluid and that when it became latent it hid itself away somewhere in the interatomic spaces of matter and ceased to be longer sensible heat. It came into existence in the same manner and occupies the same place in the science of heat that the word current does in the science of electricity. Both of them are misnomers. When the ice is all melted, potential energy is no longer stored, but is manifested in the sensible heating of water, the degree of which is measurable by the thermometer until it reaches the boiling point, where it is again arrested. All of the surplus heat above that temperature is consumed in rendering the liquid water into moisture globules that float away into the air, each one of them charged with a store of potential energy. Let us follow this vapor spherule as it floats into the upper regions of the atmosphere. Myriads of its fellows travel with it until it reaches a point where condensation takes place, when it collapses and unites with other vapor particles to form water again. In doing this, the heat that was expended upon it to disengage it, whether the heat was artificial or that of the sun's rays, now reappears either as sensible heat or as electricity, or both. And this is what is meant in meteorology by latent heat becoming sensible heat at the time of condensation. In fact, it is stored or potential energy becoming active or kinetic, and assumes the form of heat or electricity as before stated. We have thus reviewed the matter of the foregoing chapter in order to follow the course of the stored energy from the melting of the ice to the vapor and back again to water. to doubly impress the fact that the energy used was not consumed, but still exists and is ready for further work. During the progress of a hailstorm, it has been stated, one of the factors that is active to produce this phenomenon is the intense ascensial force that is given to the moisture-laden air caused by intense heat at the surface of the earth. This condition forces the moisture vapor to higher regions of the atmosphere than is the case with the ordinary thunderstorm. Another factor that is undoubtedly active in producing hail under these circumstances is that when condensation takes place in the higher regions and is therefore more energetic on account of the intenser cold, the potential energy that is set free by the moisture spherules takes in a larger degree the form of electricity rather than heat, as is the case under more ordinary circumstances. While in the end this electrical energy becomes active heat, it does not for the time being, and thus favors the ready congelation of the condensed moisture into hailstones. Hailstorms are always attended by incessant thunder and lightning, and this fact favors the theory advanced above. It will be easily seen from a study of the foregoing what a wonderful factor evaporation, which is a product of the sun's rays, is in the play of celestial dynamics. It ascends from the surface of the earth or ocean laden with a stored energy, the power of which no man can compute, and beside which gravitation is a mere point. In the upper regions of atmosphere this potential force under certain conditions is released and becomes an active factor, not only in the formation of cloud and the precipitation of rain, hail, and snow, but it disturbs the equilibrium of the air and sets that in motion. Certain physicists deny that evaporation has anything to do with atmospheric electricity. They tell us that it is caused by the arrest of the energy of the sunbeam by the clouds and vapor in the upper atmosphere. We admit that a part of the energy is so arrested and is stored for the time in moisture globules by a process of cloud evaporation to transparent vapor again, yet this does not hinder the same process from going on at the surface of the earth wherever there is water or moisture. But they tell us that the electroscope does not show any signs of electrification in the evaporated moisture. Of course it does not. The electroscope is not made to detect the presence of energy except when set free as electricity. A wound-up spring does not seem to be electrified, but if it is released, the energy stored in it will be transformed into electricity if the conditions are right. Just so, the energy required to put the moisture spherule into a state of strain is latent until some power releases it, when it reappears as active energy of some form. We have now followed the relation of heat to water from a point 10 degrees below freezing up to where it was forced into its original gases, oxygen and hydrogen. These gases have stored in them a wonderful amount of potential energy. When 1 pound of hydrogen and 8 pounds of oxygen unite to form water, the mechanical value of the energy given up at that time in the form of heat is represented by 47 million pounds raised to 1 foot in height. And this is the measure of the energy that was put into 9 pounds of water to force it from a state of vapor into its constituent gases. After the combination of the gases into a state of vapor, the temperature sinks to that of boiling water. The amount of energy given up in condensing the 9 pounds of vapor into 9 pounds of water is equal to 6,720,000 foot-pounds. If this 9 pounds of water is now cooled from the boiling point to 32 degrees Fahrenheit, we come to the final fall, where the potential energy that is stored in the operation of melting ice is given up suddenly at the moment of freezing, which in 9 pounds of water is 993,546 foot-pounds. Professor Tyndall, in speaking of the amount of energy that is given up between the points where the constituent gases unite to form 9 pounds of water and the point where it congeals as ice, says, quote, "Our 9 pounds of water, at its origin and during its progress, falls down 3 precipices. The first fall is equivalent in energy to the descent of a ton weight down a precipice 22,320 feet high over 4 miles. The second fall is equal to that of a ton down a precipice 2,900 feet high, and the third is equal to a fall of a ton down a precipice 433 feet high. I have seen the wild stone avalanches of the Alps, which smoke and thunder down the declivities with a vehemence almost sufficient to stun the observer. I have also seen snowflakes descending so softly as not to hurt the fragile spangles of which they are composed. Yet to produce from aqueous vapor a quantity which a child could carry of that tender material demands an exertion of energy competent to gather up the shattered blocks of the largest stone avalanche I have ever seen and pitch them to twice the height from which they fell." Unquote. When we contemplate the foregoing facts as related to so small an amount of water as 9 pounds, and multiply this result by the amount of snow and rainfall each year, and the amount of ice that is congealed and again liquefied by the power of the sun's rays, we are appalled and shrink from the task of attempting to reduce the amount of energy expended in a single year to measurable units. Having considered water in its relation to heat in the preceding chapters, we will now take up the subject of water in its relation to ice and snowfall and the phenomena exhibited in ice rivers, commonly called glaciers. When water is under pressure, the freezing point is reduced several degrees below 32 degrees Fahrenheit. This fact has been determined by confining water in a close vessel and putting it under pressure and subjecting it to a freezing mixture, and by this means determining the freezing point under such conditions. By putting a bullet or something of that nature into the water that is subjected to pressure, one can tell by shaking it when the freezing point is reached. If water is put under pressure and cooled to a point below 32 degrees and yet still remains in the liquid state, it may be suddenly congealed by taking off the pressure. This shows that the pressure helps to hold the molecules in the position necessary for the liquid state and prevents the rearrangement of them that takes place at the moment of freezing. When the water molecules are arranged for the liquid condition, they may be compared to a spring that is wound up and held in position by the heat energy that is stored in the water. And when this energy is given up to a certain degree, the power that holds the spring wound up is suddenly released, when it unwinds and occupies a larger space. There is a force that we may call polar force, which is constantly tending to push the molecules of water into an arrangement such as we can see when crystallization takes place, as it always does in the act of freezing. These polar forces cannot act so long as the energy in the form of heat is sufficient to hold the water in the fluid state. But the moment this energy, which tends to hold it in the fluid state, falls below that which tends to rearrange it into the crystalline form, it is overcome by the superior power of the latter force, and we have the phenomenon of solidified water. A very interesting experiment may be performed with a block of ice by anyone when the ice is near the melting point. If a wire is put around the ice and a sufficient weight is suspended to it, the pressure of the wire on the ice will gradually liquefy that portion immediately under the wire, which allows it to sink into the ice slowly, and as this process goes on the ice freezes together again behind the wire, so that in time the wire will pass entirely through the block and leave it still a solid block as it was before the experiment began. This is an interesting fact which it will be well to remember when we come to explain glacial action, or rather the law that governs glacial action. If we take two pieces of melting ice and bring them together, they immediately congeal at the point of contact. This phenomenon is called regelation. Ice has some of the properties of a viscous substance. It will yield slowly to pressure, especially when near the melting point, but if put under a tensional strain it will break, as any brittle substance will, so that it has the properties of both viscosity and brittleness. Ordinarily we are in the habit of treating water as a fluid and ice as a solid, But from what has gone before the reader must understand that in a certain sense ice should be treated as having semi-fluidic. Gray, Chapter 24. Why does ice float? Nature is full of surprises. By a long series of experimental investigations, you think you have established a law that is as unalterable as those of the Medes and Persians, but once in a while you stumble upon phenomena that seems to contradict all that has gone before. These, however, may be only the exceptions that prove the rule. It is recognized as a fundamental law that heat expands and cold contracts, that the atom when in a state of intense motion, which is the condition producing the effect that we call heat, requires more room than when its motions are of a less amplitude. In other words, an increase in the amplitude of atomic motion is heating, while a decrease is cooling. It follows from the above statement that the colder a body becomes the smaller will be its dimensions. There are 2 or 3 and perhaps more exceptions to this rule, and the most notable one is that of water. Water follows the same law that all other substances do under the action of heat and cold, within certain limits only. If we take water, say at 50 degrees Fahrenheit, and subject it to cold, it will gradually contract in bulk until it reaches 39 degrees Fahrenheit. At this point, very curiously, contraction ceases, and here we find the maximum density of water. If the temperature is still lowered, we find the bulk is gradually increasing instead of diminishing, as is the rule with other fluids, and when it reaches the freezing point there is a sudden and marked expansion, so much so that a cubic foot of ice, which is solidified water, will not weigh as much as a cubic foot of water before it freezes. Hence it floats. Let us try an experiment. Take a small glass flask terminating in a long neck, say of 4 to 6 inches, and of small diameter. Suppose the water in the glass to be at 50 degrees Fahrenheit. Fill the flask with water until it stands halfway up the neck at 50 degrees temperature. Now immerse the flask gradually in hot water and observe the effect. For a moment the water will lower in the neck of the tube, but this is due to the fact that the glass expands before the heat is communicated to the water, and enlarges its capacity. But immediately the water will begin to rise as the heat is communicated to it, and will continue to expand up to the boiling point. Now take the flask out of the hot water and gradually introduce it into a freezing mixture made of broken ice and salt. Immediately the water will begin to fall in the tube, showing that it is contracting under the cold, and it will continue to contract until it reaches a temperature of 39 degrees Fahrenheit, when it will come to a standstill and then proceed to expand as the temperature of the water lowers. When it reaches the freezing point, the fluid can no longer rise in the neck of the flask, which is broken by the sudden expansion that takes place at this point. To show what an irresistible power resides in the atoms of which the body is made, let us take an iron flask with walls 1/2 inch or more in thickness. Fill it with water and seal it up by screwing on the neck and iron cap. Now plunge it into the freezing mixture, and the first effect will be to contract the water unless it is already below 39 degrees Fahrenheit. But when it reaches that point, expansion sets in, which continues to the freezing point, when a greatly increased expansion takes place suddenly. The walls of the iron flask, although 1/2 inch in thickness, are no longer able to resist the combined efforts of the billions upon billions of the atoms of which the water is made up, in their individual clamor for more room. Hence the flask is shivered into pieces. There are 1 or 2 other substances which are exceptions to the general rule, but we will mention only one, which is the metal bismuth. If we should melt a sufficient amount to fill an iron flask, such as we have described, and subject it to the same freezing process, the flask will be broken the same as in the experiment made with the water. A query arises: why this phenomenon? Why does water follow a different law in cooling from that of nearly all other substances? This is a case where it is much easier to ask a question than to answer it. When water solidifies at the moment of freezing, crystallization sets in. But what is crystallization? Crystallization is a peculiar arrangement of the molecules of matter which takes place in some substances when they pass from the liquid to the solid form. The molecules assume definite forms and shapes according to the nature of the substance. When water assumes the solid form under the actions of cold, the molecules arrange themselves according to certain definite and fixed laws, the result of which is to increase the bulk to a considerable extent over that which the same number of molecules would occupy at a temperature of 39 degrees Fahrenheit. Hence, as has been heretofore stated, a given block of solidified water is lighter than the same bulk would be in the fluid state, and this is the reason why ice floats. What would happen in case nature did not make this exception to the laws of expansion and contraction by heat and cold in the case of water? First, our lakes would freeze from the bottom upward. As soon as the surface became frozen or even colder than the water underneath, it would drop to the bottom, the warmer water below coming up by a well-known law that the warmer fluid rises and the colder falls. This circulation would continue until ice began to form, which would immediately drop to the bottom, and this process would go on until the whole mass were frozen solid. In the same way, our rivers in the northern climates would freeze from the bottom, and in time our valleys would fill up with ice to a thickness that the summer's sun would never melt, and gradually all north of a certain zone would become a great glacier, rendering not only the lakes and rivers but also the surface of the earth unfitted for animal life. Those who believe that the laws of nature are the creations of a beneficent and all-wise intelligence will see in this exception to the general law in the case of freezing water a striking evidence of design. But those who have no such belief will say it is a most fortunate, though fortuitous, circumstance, a saying they will have to make regarding thousands of other things in nature, and go on floundering in the interminable sea of I don't know. The atom, when it is acting under the direction of a fixed law, is a giant in strength, and when its individual strength is multiplied by billions upon billions, the combined energy exerted produces a power that is irresistible. Not only has nature endowed these atoms with this wonderful power, but she has also willed that they arrange themselves in lines of beauty. In confirmation of this, we need only to study the work of the frost upon our window panes. As we lie in our beds on a cold night and exhale moisture from our lungs, it settles upon the window panes of our bedrooms, where nature, that wonderful artist, forms it into beautiful pictures that gladden our eye when we awake. Most beautiful things there are flowers and trees, and bevies of birds, and swarms of bees, and cities, and temples, and towers, and these all pictured in silver sheen. Chapter 25. Glaciers. Glaciers are rivers of ice, and like other rivers, some of them are small and some very large. They flow down the gorges from high mountains, whose peaks are always covered with a blanket of eternal snow. Summer and winter the snow is precipitated upon these mountains, and from time to time the heat of the sun's rays softens the snow, when by its great weight it packs more closely together until it is, in many cases, formed into solid ice cakes. If we take a quantity of snow or a quantity of granulated ice and put it under a sufficient pressure, we can produce clear, solid ice, and it is by this process that ice is formed out of the snow and hail that falls continually upon the tops of these glacial mountains. We have seen that ice possesses certain viscous or semi-fluidic properties, and that it will yield to pressure. But if we put it under sufficient tensional strain, it snaps like glass or any other brittle substance. As the snows upon these mountains pile up higher and higher, the pressure becomes greater and greater until it reaches a point where the mass begins to move gradually down the mountainside, following the gulches and defiles that furnish a path of least resistance to its flow. At the sides and bottom, where there is contact with the earth, the movement is slower than it is at the surface and in the middle of the ice stream. If there were no curves in the ravine or gulch through which it flows, the point of greatest movement would be confined to the middle of its width. But in flowing through a winding gulch the most rapid flow follows the lines of greatest pressure, and this line is deflected from side to side, so that the line of greatest flow is more winding than is the bottom of the valley through which it flows. The movement is called a flow, but it is very sluggish, only a few inches in a day, as will appear later. If the bottom and sides of the valley were straight, the surface of the ice would be comparatively even. I say comparatively, for as compared with a smooth surface it would be very rough, but there would be none of the great crevices or openings now to be found in the ice, which sometimes are very large and extend to a great depth. If in its downward course the bottom of the ravine suddenly becomes steeper, the top of the ice is put under a tensional strain which causes it to break, thus forming the crevasses. If at the bottom of the descent the valley curves upward or preserves the straight line for a considerable distance, these crevasses will close at the top and perhaps open at the bottom, and the blocks of ice will freeze together to such an extent that the water caused by the melting ice will flow on top until it comes to another crevasse, where it runs through to the bottom or underflow, which is always an attendant of a glacier. The glacier continues its flow down the mountainside till in some cases it reaches quite to the valley below, and in others it stops short, as the action of the sun is so great that it melts entirely away at this point as fast as it moves down. In the winter time, however, the glacier may flow far down into the valley and will accumulate greatly in bulk, owing to the fact that the ice forms from the precipitation of snow on top faster than it melts away underneath. If it were not for the fact that in summer the glaciers melt faster than they form, the whole valley would in time become a great river of ice. It is the case in Switzerland that some years the accumulation is greater from snowfall than diminution from melting. If this condition should continue, it would become a serious matter. In the downward flow of a glacier, slow as it is, there is an exhibition of wonderful power. Great boulders are torn from their beds and either ground to powder or carried down to the end of the glacier, to be dropped with the other debris that has been carried there by the same force, forming an accumulation that geologists call the moraine. Of these moraines we will speak more fully later on. It was the privilege of the writer some years since to visit the great glaciers of Switzerland and to some extent study their action. Some rivers have their origin chiefly in melting glaciers. They start as ice rivers and end in rivers of water. The effects during the great ice age of some of these glacial rivers, which are now extinct, are very remarkable. We shall have occasion to refer to them when we come to treat of the glacial period. There is a glacial river flowing which is fed largely by the great Rhone glacier in Switzerland. The water from this river is almost as white as milk, which is occasioned by the grinding action of the great ice blocks on the rock as it flows down the sides of the mountain. These glacial rivers are much higher in summer, of course, than in winter, some of them having not only an annual fluctuation but a diurnal one. The former is caused by the cold of winter, and the latter because it freezes to some extent at night and checks the flow of water. The difference between day and night in these high altitudes is very marked. While it is extremely hot in the sun, it is cool the moment we step into the shade. I remember walking across one of the glaciers in the Alps called the Mer de Glace one clear day in summer when I suffered so much from the heat, although standing upon a sea of ice, that it was necessary to carry an umbrella. In fact, during my stay there was a case of sunstroke that occurred upon this same glacier. This intense heat during the day melts the surface of the ice, which forms streams that run along on the top of a glacier until they come to a crevasse or riffle in the ice river, where they plunge down and become a part of the glacial stream that is flowing underneath the ice. The speed at which these ice streams flow varies greatly with the size of the glacier as to width and depth, and the steepness of the grade, and many other conditions. In its movement the glacier is constantly bending and freezing and being torn asunder by tensional strain, yielding and liquefying at other points by pressure, only to freeze again when that pressure is removed. This, taken in connection with the friction of the great ice boulders, produces a movement that is exceedingly complicated in its actions and interactions. According to Professor Tyndall's investigations, the most rapid movement observed in the glaciers of Switzerland is 37 inches per day at the point of greatest movement. From this point each way the motion gradually diminishes until it reaches the sides of the glacier, where the motion is not more than 2 or 3 inches. The great North American glaciers move at a much higher rate of speed. We are indebted to Dr. G. Frederick Wright, author of The Ice Age in North America, who spent a month studying the Muir Glacier in Alaska, for many details concerning that great ice river. This glacier empties into Muir Inlet, which is an offshoot of Glacier Bay. It is situated in latitude 58 degrees 50 minutes and longitude 136 degrees 40 minutes west of Greenwich. The bay into which this glacier empties is about 30 miles long and from 8 to 12 miles wide. This bay, with its great glacier, has a setting of grand mountain peaks. I cannot do better than to quote the words of Dr. Wright when he describes the location of this glacier. Dr. Wright lived for a month in a tent on the edge of this bay, a short distance below the face of the great glacier, where the icebergs fell off every few minutes into the deep water. He says, quote, "To the south the calm surface of the bay opened outward into Cross Sound 25 miles away. The islands dotting the smooth surface of the waters below us seemed but specks, and the grand vista of snow-clad mountains guarding either side of Chatham Strait seemed gradually to come to a point on the southern horizon. Westward toward the Pacific was the marvelous outline of the southern portion of the St. Elias Alps, the lofty peaks of Crillon, 15,900 feet high, and Fairweather, 15,500 feet high, about 25 miles away and about the same distance apart, stood as sentinels over the lesser peaks." Unquote. The Muir Glacier might be likened to a great inland sea of ice fed by many tributaries or ice rivers. It narrows up at the point where it empties into Muir Inlet to 10,664 feet, or a little over 2 miles. An enormous pressure is exerted at this point, which causes the ice to flow in the central portion at the rate of about 70 feet per day. There is a continual booming, like the firing of a cannon going on, caused by the bursting of some great iceberg, either before it takes its final leap into the water or at the moment of its fall. At the point where these great icebergs drop off into the water they stand like a solid wall 300 feet above its surface. Dr. Wright says, quote, "From this point there is a constant succession of falls of ice into the water, accompanied by loud reports. Scarcely 10 minutes, either night or day, passed during the whole month without our being startled with such reports, and frequently they were like thunderclaps or the booming of cannon at bombardment of a besieged city, and this though our camp was 2½ miles below the ice front. Repeatedly I have seen vast columns of ice, extending up to the full height of the front, topple over and fall into the water. How far these columns extended below the water could not be told accurately, but I have seen bergs floating away which were certainly 500 feet in length." Unquote. It is estimated that the cubical contents of some of these icebergs are equal to 40,000,000 feet. This great glacier is fed by the constant precipitation of snow upon the sides and peaks of the high mountains that surround its vast amphitheater, which is floored with icebergs. Wonderful as this seems to us today, it is scarcely a microscopic speck of what existed during the ice age all over the northern part of North America. There are many other great glaciers in the mountains of the Pacific coast. Some years ago I saw one of these immense glaciers in British Columbia, from a point called Glacier Station in the Selkirk Mountains on the Canadian Pacific Railroad. It was during the month of August, when all of the region was pervaded by a dense smoke occasioned by burning forests. This glacier is a very showy one, owing to the steepness of the side of the mountain and its great breadth. All the glaciers that exist today are gradually receding, and are destined eventually to entirely disappear, unless there is a change in meteorological conditions, which some scientists claim will be the case if we only wait long enough, when again all this northern country will be covered with a great ice sheet. There is no doubt in regard to the facts concerning a glacial period that must have existed in the ages past. To anyone who has made a study of the subject there is not wanting abundant evidence to prove that this northern country was at one time enveloped with a great ice sheet of enormous thickness. The conditions that existed to bring about such a state of things have been the subject of much speculation by philosophers, but no one as yet has arrived at any very satisfactory conclusion. Many theories have been advanced, some of them not worth considering, while others have many things that give them a show of plausibility. But all of them have what is said of the Darwinian theory, a missing link. It will be interesting, however, and also instructive to know what can be said in favor of a set of conditions that would produce such momentous. Chapter 26: Evidences and Theories of an Ice Age. There is abundant and unassailable evidence that at one time, ages ago, a vast ice sheet covered the whole of the northern part of North America, extending south in Illinois to a point between latitudes 37 and 38. This is the most southerly point to which the ice sheet reached. From this point the line of extreme flow runs off in a northeasterly and northwesterly direction. The northeasterly line is through southeastern Ohio and Pennsylvania, striking the Atlantic Ocean about at New York, thence through Long Island and up the coast of Massachusetts. Northwesterly it follows the Mississippi River to its junction with the Missouri, which it crosses at a point some miles west of this junction, following the general course of this river a little south of it through the states of Missouri, Nebraska, Dakota, and Montana. The lines, especially the northeasterly one, are very irregular, shooting out into curves and then receding. This line of extreme ice flow is marked by glacial drift so prominently that no one who has studied glacial action can doubt for a moment what was the cause of these deposits. The line is called the terminal moraine. By examining a map of North America and tracing the line of the moraine as we have described it, it will be seen that about 2/3 of North America was at one time covered with ice to a greater or less depth. How deep is simply a matter of conjecture, but in the central portions of the great glacier, where was the bulk of snowfall, it must have reached a depth of several miles to account for the enormous pressure that would be required to carry the ice so far southward. But let us go back and define what is meant by a moraine. A moraine is a name given to the deposits that are of stone, gravel, and earth, that have been carried along by the movement of the glaciers and deposited at their margins, sometimes piled up to great depths. The composition of these moraines is determined, of course, by the nature of the country over which the stream of ice is flowing. Boulders of enormous size have been carried for hundreds of miles, and the experienced geologist is able to examine any one of them and tell us where its home was before the glacial period. Moraines are divided into different classes according to their position and constitution. The moraine found at the extreme limit of ice flow is called the terminal moraine, as before mentioned. Those that are found inside of this line and between two flows are called medial moraines. There is a subdivision called kettle or gravel moraines, which are very prominent in northern Illinois and southern Wisconsin, and may be said to culminate in the vicinity of Madison. This moraine is a great deposit of gravelly soil. Where this moraine exists, the face of the country is covered with kettle holes of all sizes and shapes, and in some of them there are small lakes, while others are dry. The great chain of inland lakes that are found in southern Wisconsin and northern Illinois were formed by deposits of ice that had been covered by glacial drift, gravel, and otherwise, brought down and deposited upon these masses of ice, which gradually melted away, leaving a depression at the points where they lay, while the drift that was piled around them loomed up and became the shores of the lake. This is substantially Dr. Wright's theory, who studied the formation of these kettle holes at the mouth of the Muir Glacier. This enthusiastic glacialist has spent many summers tracing the terminal moraine with its fringe along the lines heretofore indicated. He is, therefore, entitled to speak with authority on matters of glacial action. The part of the country that has been plowed over by these glaciers is called the glaciated area, and the rest the unglaciated. The whole of North America, north of the line of the terminal moraine that we have traced, is a glacial region, with the exception of a few hundred square miles, chiefly in Wisconsin, where the ice seemed to have parted and passed around this area, coming together again on the south side of it. The ice probably did not reach the extreme limit that shows glacial deposit, but undoubtedly the effects of it are seen for some distance to the south, owing to the fact that during the time it was melting great quantities of water flowed away from the extreme edge of the ice, carrying with it more or less of the glacial drift, which was deposited for some distance to the south. When the ice receded, it undoubtedly paused at different points, where it remained stationary for a long period of time. I mean stationary at its edges, for the flow of ice was continually moving, but in its progress southward it came to a point where the heat was sufficient to melt the ice as fast as it arrived at that point. The onmoving ice was continually bringing with it the debris that it had gathered up at different points on its journey, so that it is easy to see how these moraines could accumulate to a greater or less depth at the margin of the ice flow, which would be determined by the duration of the period it remained stationary. This, however, is only one factor, as the surface of the earth in some parts of the country would be more easily picked up and carried than in others. Therefore, the drift accumulated much more rapidly in some sections than in others. Another factor that was active in the more rapid accumulation at certain points was the speed at which the ice moved, and this would be determined by the pressure that was behind it, and there would always be lines of unequal pressure existing in such a great glacier as must have existed when these moraines were formed. As an instance of the difference in the glacial deposits that are made in different periods during the time of the melting of the great ice sheet, we may compare the kettle moraines of Wisconsin with the clay deposit mixed with broken gravel that we find along the west coast of Lake Michigan. Those whose homes are situated between Winnetka and Waukegan on the lake shore have the foundations of their houses set in glacial drift that was shoved into position by the ice during the glacial period. Anyone who makes an examination of the bluffs along the shore of this lake will notice that there is no stratification whatever to the deposit, such as will always be found in an unglaciated region. Going west from the bluff a few miles, we come down to the prairie level, where we find the soil of an entirely different nature. The soil of the prairies of Illinois and Iowa is probably to a great extent a water deposit. It is the kind we find in the bottom of a pond that has stood for many years, and it would seem that at some period all this prairie country with the black soil was the bottom of a great lake. The facts of a glacial period are beyond question, but when it occurred and how it occurred are questions that many have tried to answer. So far, all that we can say of them is that some of them are shrewd guesses. The evidences adduced for determining the time are the erosion caused by rivers and streams since the ice subsided. Some of the rivers and outlets of lakes had their courses changed by the action of the ice, so that when it subsided new watercourses were formed, and the erosion that they have produced from that time to the present furnishes the data for determining the time since the subsidence of the ice at any particular point. For instance, Niagara Falls was undoubtedly at one time situated at Queenstown, a number of miles below its present position, and the time that it has taken to grind out the great gorge that exists between that point and the present falls is approximately a measure of the time that has elapsed since the subsidence of the ice at that point. Various estimates have been made to determine the rate of erosion. The earlier ones put the time at about 35,000 years, but there are later investigators who make the time much shorter, not over 10,000 years. So much for the time. But you ask, what about the occasion or cause? This is a question that many have attempted to answer, there having been 8 or 10 theories promulgated with regard to the cause of the glacial period, but no one of them is entirely satisfactory, and only 2 or 3 of them are deserving of much discussion. It is always interesting to know what people think, however, even if we do not agree with them. The first theory named is that the glacial period is due to the decrease of the original heat in our climate. This theory can be dismissed by saying that the planet was cooling at the time and has been cooling ever since, and that the reasons for an ice age are greater now than then on that theory. Another theory assumes that at some former period there was a greater amount of moisture in the atmosphere. While this, of course, would be the occasion for greater precipitation of snow, it does not account for the changing conditions that would produce the ice effect. That there was a preglacial period there is abundant evidence in buried forests and the filling up and changing of river beds and other evidences that will be referred to further on. This theory, unmodified and stated broadly, is not satisfactory. Another way of accounting for the glacial period is the change in the distribution of land and water, which is supposed to affect the distribution of heat over the earth's surface. There is much in this theory that commends itself as plausible. Another theory supposes that the land in northern Europe and America was elevated to a higher level at that time than it is now. Others attribute it to variation of temperature in space and of the amount of heat radiated by the sun. The final theory for accounting for the ice age is attributed to what is termed the precession of the equinoxes. In short, the precession of the equinoxes means that the division between summer and winter is changing gradually, so that during a period of 10,500 years the summers are growing longer in the northern hemisphere and the winters shorter. We are now in the period of long summers, but in another 10,000 years we shall be in the period of short summers and long winters. This difference of time between the winters and the summers is supposed to be sufficient to change the thermal conditions sufficiently to produce an ice age. It is true that the conditions now are very evenly balanced, so much so that in Switzerland the glaciers will increase for some years together, when the conditions will change, causing them to gradually recede. Several of the theories that have been advanced present evidences that are entitled to careful consideration, but none of them can be said to be entirely satisfactory. It is well known that the chief factors in the production of glaciers are moisture and cold. Cold alone is not sufficient, neither is moisture, unless we can precipitate it in the form of snow. Cold is opposed to the production of moisture, and this is a flaw in the argument presented by the last theory, unless we can couple with it another set of conditions which we will discuss later. The solution, if it is ever reached, is perhaps more likely to be found in the realm of meteorology than geology. It is unnecessary to change the conditions of temperature or the amount of moisture now existing in order to produce the great glacier again, provided this moisture could be precipitated, enough of it, in the right place as snow. For instance, if in Switzerland, where the conditions are nearly balanced, the annual precipitation could be slightly increased, we should have a condition that would precipitate more snow in winter than would melt in summer, and the glaciers would gradually accumulate in size until they would fill the valleys and gorges to the same extent as formerly prevailed. There only needs to be such a change in the meteorological conditions as will cause a greater precipitation in that part of the globe, favorable to glaciers, as, for instance, in the northern part of North America toward Alaska. This might be produced by a change in the conditions of the equatorial current, so that evaporation would be more rapid in the northern Pacific than it now is. When we consider that evaporation increases in proportion as the heat increases, we can see that heat is just as important a factor in the production of glaciers as cold. If evaporation could be increased in the Pacific Ocean west of Alaska, which would be carried by the wind over the mountains upon the land and precipitated as snow, the great glaciers in that region would begin to grow instead of gradually receding as is the case at present, and this without any change in the temperature of the world as a whole or in the amount of heat received from the sun. One can readily see how changes in the elevation of the bottom of the ocean would have such an effect upon the tropical stream as would either increase or decrease the temperature of the thermal river that flows up the western coast of Alaska. Whatever may have been the cause that created the great ice age in North America, so that a sheet of ice covered considerably more than half of the continent, there is no doubt in regard to the fact of the existence of such an age, and it will be interesting to study some of the physical changes that have been made by the ice at that period on the surface of the glaciated area.
Chapter 27: Glacial and Preglacial Lakes and Rivers. Since the recession of the ice, preglacial lakes have been filled up and are now dry land, and river beds have been changed so that new channels have been cut and new lakes have been formed. Even the imagination, that wonderful architect, with all its tendencies to exaggeration, palls in its attempt to give expression in measured quantities to the mighty power exerted by the great glacier or combination of glaciers that existed in comparatively recent times. I say recent times because even 10,000 years is only a mere point of time when compared with the actual age of our globe. Some years ago, in company with Dr. Wright, author of The Ice Age in North America, I visited Devil's Lake near Baraboo, Wisconsin. At this point are striking evidences of the work of the Ice Age. Before the glacial period, the Wisconsin River made a detour some miles west of its present channel through the high hills in the region of Baraboo. The hills on each side of Devil's Lake are very precipitous and are formed almost entirely of rocks. The river at that point passed between two of these hills. When the ice flowed down, it surrounded these hills, yet did not sweep over their tops, but left great piles of glacial drift, both at the points where the river channel entered the hills and where it emerges from them. The channel between the hills was protected and not filled with the debris. Therefore a deep basin was left, which is kept filled by the watershed furnished by the surrounding hills. This lake recedes many feet during the summer, but it is again filled up by the rains and snows of winter. There is no considerable stream either flowing into or out from it. It is a lake formed by the glaciers, but in a different way from those in the gravel deposits at other parts of southern Wisconsin and northern Illinois. There are hundreds and perhaps thousands of lakes that have been formed in one way or another through the power of glacial action. These smaller inland lakes, so many of which are seen in northern Illinois, southern Wisconsin, and Minnesota, are due almost entirely to the great deposits of glacial drift that have been transported with the ice. Wherever these kettle holes are found, large bodies of ice have become anchored, while the ice behind it has carried the drift until it is covered over and piled up at the sides. When these ice mountains melted away, depressions were left, which in some cases have resulted in lakes, and in others simply dry kettle holes. This process has been hinted at in a former chapter, but we give it here as one of the kinds of lakes formed during the glacial period. They are found everywhere that glacial action has prevailed. They are found in great abundance in some parts of New England on the margin of the terminal moraine. These lakes, however, are comparatively insignificant as compared with the great inland seas like Lake Superior and Lake Michigan, that undoubtedly owe their origin largely to the Ice Age. There are other factors, however, that enter into the formation of the great chain of lakes on the northern boundary of the United States, besides those mentioned, that have brought into existence the smaller inland lakes. Glacial lakes may be divided into three classes: those found in the kettle holes of the terminal or medial moraines, and those that are formed by the deposition of the glacial drift, as, for instance, Devil's Lake, and those that are caused by ice forming dams across the valley of a river that lasted only during the Ice Age. In some lakes of the second class, erosion undoubtedly entered into their formation, as well as the piling up of glacial drift. In order, however, that we may understand more fully the formation of these greater lakes, it will be necessary for us to go back and examine the conditions that seem to have existed before the glacial period. It is a fact well known that continents have periods of elevation and depression. There is abundant evidence that the northern portion of the North American continent was elevated to a much higher level in preglacial times than it occupies now. This is evidenced in very many ways by sounding the depths of old river beds, now filled with glacial debris. The old beds show unmistakable evidences of having been worn down to their present level by the action of running water. They also prove to be many feet below the present sea level. This fact seems to be sufficient to prove the theory of a higher elevation of the North American continent in preglacial times. It should be said here that undoubtedly the constant filling up of the ocean, with the drift carried down by the rivers, has somewhat raised its level, but hardly to the extent indicated by the old river beds. The question naturally arises, where did all the dirt come from to fill up these great river beds and change the whole topography of the northern half of the continent? Dr. Wright estimates that there is not less than 1 million square miles of territory in North America covered with glacial debris to an average depth of 50 feet. Of course, the depth varies in different places from a few inches to several hundred feet. Of the carrying power of these great glaciers, we will speak more fully in a future chapter. In preglacial times, the watershed of the Mississippi and of the great rivers east of the Allegheny Mountains, the Susquehanna and Hudson, extended probably farther north than it does today. The larger portion of the drainage area that now finds an outlet through the river St. Lawrence at one time undoubtedly drained off through the Mississippi Valley into the Gulf and the Valley of the Mohawk into that of the Hudson. It is supposed by those who have made this branch of geology a study that prior to the glacial period a river flowed down through Lake Superior, which connected with Lake Michigan at a point near its present outlet at Sault Ste. Marie, the channel of the river passing down through what is now the bottom of Lake Michigan, which had an outlet at the head of the lake near Chicago, and flowed off into the Mississippi River. All of the lake bottoms of this great chain, with the exception of Lake Erie, are now below sea level. The reason for this exception will appear further on. Before the Ice Age, there was supposed to be no connection between Lake Michigan and Lake Huron, as there is now, through the Straits of Mackinac. Another preglacial river had its rise in the region of Lake Huron and flowed through an old riverbed extending from the Georgian Bay in a southeasterly direction through the province of Ontario and emptied into the present Lake Ontario. From Lake Ontario there is an old riverbed running through the valley of the Mohawk, which empties into the Hudson at Troy. Neither of these two rivers, having their sources in the north, found an outlet through the present St. Lawrence River. During the time of the glacial period, there is evidence that there was more than one center of snow and ice accumulation, and each of these great centers probably had several subcenters. This theory has color given to it by the directions of movement shown by the glacial drift. The rounded appearance of boulders was caused by the grinding action of the ice. These boulders, when they were first torn from their rocky beds by the irresistible power of ice pressure, were rough and jagged in shape, the same as any rock would be, torn from a quarry by a blast. They have been smoothed and rounded by rubbing against the moving ice and against each other in the progress of their long journey from their original homes. Where their home was, the geologist can immediately tell upon examination. It is only necessary then to examine the boulders of any particular locality to determine the direction of the ice flow at that point. There seem to have existed centers of ice accumulation to the north of all the Great Lakes, and when they had grown to a sufficient height they joined at their edges, making one grand glacier, the movements of which were the resultant of the combined pressure exerted by these great centers of power, so that all of North America, north of the line of the terminal moraine, with the exception of the small area, heretofore noted, chiefly in Wisconsin, became covered with one vast sheet of ice. The glacier north of Lake Superior widened out the old riverbed by a process of erosion to its present width. There may have existed something of a lake in pre-glacial times, through which the river ran, but it undoubtedly owes its present width to the grinding action of the irresistible icebergs and the piling up of debris on the shores. The riverbed was filled up by a glacial drift at the point of its present outlet until the lake was raised in its level, much higher than that of Lake Michigan. Another glacier plowed down through Lake Michigan, widening it out to its present dimensions, while the glacial drift was deposited at what is now the head of the lake, filling up the old outlet and thus making a great dam. The damming up of these great watercourses was another cause for increasing the width of these lakes. In a similar way, Lake Erie was formed. It is supposed, however, that this lake is entirely the product of glacial action, as there is no evidence of an old riverbed in its bottom. Besides, it is much shallower than the other lakes. The same action that formed Lake Erie filled up the old riverbed, running through the province of Ontario, so that when the ice receded, Lake Erie became the new channel for the old river. The same process filled up the valley of the Mohawk to more than 100 feet in depth, and also raised the valley of the Hudson. This caused the new channel to be made through the Niagara River and a new route to the ocean for the drainage of all the chain of lakes through the St. Lawrence. It will be seen that the bottoms of all these great lakes to a certain extent were worn out by the action of running water, except Erie. The great glaciers widened them out, and in the case of Lake Erie scooped it out. At the same time it built great dams across the outlets, which raised the surface of the water to a much higher level, and caused them to form new outlets, thus changing the whole face of the country over which the ice drifted. The glaciated region of North America is among the most productive in the world, and in many respects presents a most pleasing landscape. Other lakes besides these mentioned have been formed during the ice period through blocking the course of a river by the ice itself. Dr. Wright, during the time he traced out the line of the terminal moraine, discovered that the ice sheet crossed the Ohio River at a point near Cincinnati, where there is a great bend to the northward in the river. With the exception of this point and perhaps another point below, the edge of the great ice sheet kept a little north of the Ohio River. At this point, however, the ice seems to have filled the valley from hill to hill, which very naturally would form a great dam or lake in the Ohio Valley. Of course, such a lake could not be permanent, because when the ice melted away, it again opened the channel and allowed the water to flow off. Some years before this discovery was made, there were terraces found along the banks of the Ohio River and its tributaries that had been the subject of much speculation. It is well known that by the action of water from rainfall, earth, gravel, and other debris will wash down the side of a hill or mountain until it strikes a water level, and there it will build out a terrace near the level of the water surface. The width of these terraces will be determined by the time the water has stood at that level and the extent and nature of the soil from which the debris comes. The evidences that are cited, pro and con, would fill a small volume, but it is sufficient to say here that the sum of the evidence goes to show that there was an ice dam formed at a point near Cincinnati, and that it was maintained for a considerable period of time. Terraces were formed running up the Ohio and its tributaries, corresponding to the level that the water must have risen to if the valley were filled up with ice. These facts, taken with the greater fact that the ice sheet actually did cross the Ohio Valley into Kentucky, and is shown by the terminal moraine, seems to prove conclusively the existence of such a lake during the period that the ice rested at its extreme limit. The fact that in some places successive terraces are found does not disprove the theory, because it is more than likely that when the ice receded it did so in successive stages, remaining at different positions for a considerable length of time. There is abundant proof of this in the successive moraines and also in the formation of successive terraces. Some of these terraces could have been formed from other causes. It does not require any great stretch of the imagination to understand how numerous lakes, much larger than any at the present day, may have extended over large portions of the west and northwest during the period that the ice was receding. The ice did not stand with an even thickness over the surface of the glaciated area, but at some points it moved down in great lobes, which marked the lines of greatest pressure as well as the greatest accumulation. As the ice melted away, the thick bodies of ice might be many, many years in melting, and they may block the outlet to a very extensive drainage area, and thus form a great inland sea from the vast amounts of water that would come from the melting ice. All of the region about Winnipeg, in the Red River country, covering great areas of hundreds of miles in extent, is a level plain only lacking the coloring to give to one passing through it the effect of a great unruffled sea. There is no doubt but that all of this region was the bottom of a great lake at some period when the ice was receding, and this accounts for the great depth of black soil that we find in this and other regions. The soil was a water deposit, such as may be found in the bottom of any shallow lake or pond today. Thus, many thousand years ago, provision was made for the fertile areas which today are feeding the world with wheat. We can imagine that during this period, the water that flowed off through the great Mississippi must have been of enormous volume as compared to the present time. A large portion of the delta of the Mississippi, which now is a part of the states of Louisiana and Mississippi, was carried down during the ice melting period. Dr. Wright, as we have before stated, has estimated that there are 1,000,000 square miles of country that has been covered to an average depth of 50 feet with glacial drift. A very large amount of the earth that was spread over the northern portion of the United States, by leveling down hills and mountains in the northern country and scooping out the Great Lakes, has been carried much farther than to the margin of the ice sheet, and I have no doubt but that a great portion of Louisiana and western Mississippi is made of earth carried down largely during the period of melting ice and deposited in this great delta. Imagine the effect that would be produced by the giving way of an ice dam, or a great number of them at different periods, that would allow a body of water as large or larger than Lake Michigan to be drained off in a comparatively short time. When we think of it in this light, the great delta of the Mississippi is easily accounted for. There are evidences of a great lake in the Red River country of the Northwest that is much larger than any of our great lakes. The shores of this lake, the bed of which is now dry land and the heart of a great agricultural region, are well defined and have been surveyed and mapped out. When this great body of water was released, it was to the northward. For this reason, it was undoubtedly held for a much longer time than some of the lakes to the southward, where the ice melted sooner.
Chapter 28. Some Effects of the Glacial Period. There is a wonderfully interesting effect produced by the action of water during the subsidence of a glacier at Lucerne, Switzerland. Some years ago there was discovered under a pile of glacial drift at the edge of the town of Lucerne a number of deep holes worn in a great ledge of rocks that crop out at that point. One of these potholes having been discovered, excavations were continued until a large number of them were unearthed, of various shapes and sizes. I had the pleasure of inspecting some of them in the year 1881. They are situated within an enclosure called the Garden of the Glaciers. Some of these holes are 20 to 30 feet in diameter, and the same depth. There are others that are smaller in size, but all of them possess the same general characteristics. In the bottom of each one was found a boulder, and in one or two cases, two of them. The action of the water had given these boulders a gyratory motion, which gradually wore away the rock underneath, until round holes were formed to the size and depth heretofore mentioned. Where there was only a single boulder, the holes were almost perfectly round, but where there was more than one boulder, the holes were sometimes in an oblong shape. The boulders were worn down to a very small size in most cases, and were round and smooth. The probabilities are that when the action first began, these boulders were large and of irregular shape. They must have been, in order to do the enormous amount of grinding that some of them did, to produce excavations in the solid rock with a diameter of 30 feet and depth about the same. The bottoms were round like an old-fashioned pot, and the insides polished perfectly smooth. This was purely an effect of the tumbling about of the boulders by the running water from the melting ice of the great glacier that covered that region some time in the long ago. There are other effects produced in rocks during the ice flow in North America that are very interesting. Great grooves are formed in the rocks, in many cases running for long distances, that have been worn in by the cutting power of the great ice sheet during the progress of its movement. There is a great groove to be seen at Kelly's Island in Lake Erie. It will be remembered that this lake is supposed to have been formed entirely by the ice of the glacial period. In its movement across the country, which is now covered by the lake, the ice encountered a huge rock formation at Kelly's Island. Great V-shaped grooves were cut through the rock by the action of the ice, deep enough for a man to stand in. In other places the rock was planed off in the form of a great molding, a number of feet wide, with the same smoothness and accuracy as though done by a machine. Another effect of the glacial period has been the creation of numerous waterfalls throughout the glaciated area. The most notable instance is that of the Falls of Niagara. In preglacial times, the beds of all rivers and watercourses had worn down to an even slope, so that there were very few, if any, waterfalls such as we have today. As we have before stated, Niagara River, as well as the St. Lawrence River, is a new outlet for the drainage of the Great Lakes. A part of this drainage formerly had its outlet through the Mohawk Valley into the Hudson, which is now filled up with glacial drift. The evidence is so conclusive that it is no longer doubted that the Niagara River dates from the time that the ice receded from that point. When the water first began to flow through this new channel, it plunged over the high rocky cliff at Queenston, and from that time to this it has been wearing its way to the present position of Niagara Falls, a distance of about 7 miles. A vast amount of interest centers about this river because it is the best evidence we have of the time that has expired since the glacial period. A great deal of study has been given to determine the amount of erosion at the falls during a year's time. If this could be accurately determined, then by measuring the distance from the present falls to Queenston, we could easily determine the number of years since the ice period. It is difficult to determine, for the conditions may have changed. For instance, the rock at the falls today is said to be harder than it is further down towards Queenston. The estimates vary from 35,000 years to 10,000 years, that is, from a rate of erosion of 5 feet to 1 foot per year. Every science is, nearly or remotely, related to every other science. If we could determine accurately the date of the ice period, it would settle a whole lot of other questions that are related to it, and one of them is the antiquity of man. Many stone implements, such as were made and used by the aborigines, have been found at various times buried deeply under the glacial drift. These finds have occurred so often that there no longer remains a doubt but that a race of men existed on this continent in preglacial times. There are evidences that at a time long ago the temperate zone extended far north of this, and it is not impossible that what is now the continent of Asia and that of North America were joined. In fact, they come very close together today at Bering Strait. If such were the case, this continent could have been inhabited from the Old World by any overland route. This, however, is mere speculation. There are a number of factors that are taken into account in determining the period of the Ice Age besides the Niagara River and the falls. The Falls of St. Anthony at Minneapolis, which, like the Niagara, is a creature of the Ice Age, the wear of water on the shores of the Great Lakes, the newness of the rocks that are piled up on the terminal moraines, all point to a much shorter period since the Ice Age than it used to be supposed, and indicate that the time does not exceed 10,000 years. To the ordinary mind, the Ice Age no doubt seems like a myth, but to the man of science, who has made a study of all of these evidences, it is as real as any fact in history, and much more real than some of the history we read. In the former case, we are dealing with evidences that appeal to our senses, while in the latter we are dealing with the recollections of men concerning what purport to have been actual transactions, and we know enough about the human mind to make it difficult sometimes to draw the line between the actual and the imaginary. The glacial period is not only closely related to the topography of North America and parts of Europe, in the changing of riverbeds, the formation of lakes, the transportation of rock, the grinding down of mountains, and spreading the debris over thousands of miles in extent, but it is related in an intimate way to many of the sciences, such as botany and zoology. A study of the flight of animals and plants in front of the great advancing ice sheet is a subject of intense interest. The migration of great forests would seem to be an impossible thing when viewed from the standpoint of a casual observer. It is true that individual trees could not take themselves up and move forward in advance of the oncoming ice, but they could and did send their children on ahead, and when the ice had overtaken the children, there were still the children's children ad infinitum. By an examination of the map it will be seen that the land gathers about the North Pole, while the South Pole is surrounded chiefly by great oceans. As we have hinted before, in pre-glacial times the temperate zone extended much farther north than it does today, and north of that there was an Arctic zone, which today is largely covered with ice sheets, where forests, plants, and animals flourished that were fitted for an Arctic climate. When the glacial period set in, and the ice sheet began its southern journey, this zone or climate was moved southward in front of the ice, thus forming, as it were, a moving zone whose climatic conditions were similar to those of the Arctic regions, at least so far as temperature was concerned, in pre-glacial times. The ice movement was so gradual that time was given for forests to spring up in advance of it that moved southward at about the same rate as that of the moving ice. Undoubtedly, the average movement was very slow, and was probably thousands of years reaching its southernmost limit, which is now marked by the terminal moraine. Thus it will be seen that while the individual trees and plants could not move, the forest as a whole could. It was gradually being cut down on its northern limit, and as gradually it grew up on the southern limit of the zone, the ice movement being so slow that the young tree of today on the southern limit becomes a full-grown king of the forest by the time the relentless icebergs reach it and cut it down, and thus the process went on until the plants, trees, and animals of the Arctic region were driven hundreds of miles south of the great chain of lakes on the northern boundary of the United States. Many of the animals of preglacial times were unable to stand the strain of the ever-changing climatic conditions and have become extinct, but their fossil remains are left to tell the story to the present and future ages. Much of the history of those times is a sealed book, but the persevering energy of the glacialist and archaeologist is gradually turning the leaves of this old book and revealing new chapters of the wonderful story of the ice. As the ice receded, the Arctic zone again traveled northward, and many animals, plants, and trees that had survived the vicissitudes of the Ice Age traveled back with it. Some of them, however, became acclimated, and by adapting themselves to the new conditions, remained behind to live and grow with the aborigines of pre-glacial times. Some of the plants and flowers that grew in profusion immediately under the edge of the great ice sheet were unable to live under the new conditions of increased warmth that came with the retrograde movement of the ice, and either had to follow closely the receding ice or escape to higher altitudes where they found a congenial clime. Thus it is that we have Arctic plants and flowers above the timber line and near the snow line of our high mountains. In proof of this theory, it has been found that these Arctic plants do not exist upon high mountains, such as the Peak of Teneriffe, where they have been isolated from the glaciated region. The Peak of Teneriffe is situated on one of the Canary Islands, surrounded by water, so that there was no possible chance for the Arctic plants to seek refuge on these isolated elevations, such as the continental mountains furnish. Thus it will be seen that the progression and recession of the ice have not only formed great lakes, changed river beds, and covered 1,000,000 square miles of area with glacial drift averaging 50 feet in depth, making many waterfalls and giving variety to the surface of the earth, besides producing the finest agricultural region in the world, but have also given variety to our forests and plants wherever this ice sheet has extended.
Chapter 29. Drainage before the Ice Age. We have already said that during the Ice Age, river beds were changed, valleys were filled up, new lakes were made, and waterfalls created. Great as were the changes made by the carrying power of moving ice, still greater were those made in pre-glacial times, not, however, from the action of moving ice, but from running water. Erosion caused by running water has probably, during the life of the world, transported more material from place to place, from mountain to valley, and from valley to ocean than any other agency, chiefly for the reason that it has been so much longer doing its work. The valley of the Ohio River, 1,000 miles or more in length, together with the great number of feeders that empty into it, is an instance of the wonderful erosive powers of running water. The valley of the Ohio River will probably average a mile in width at its upper level, and, deep as it is today, it was much deeper in pre-glacial times. There is evidence that the whole bed of the river was from 100 to 150 feet deeper than it is at present. This has been determined by borings at different points to ascertain the depth of the drift that was lodged during the glacial period in the trough of the Ohio River. Anyone traveling up or down the river today can readily see that it is a great sinuous groove cut down through the earth by millions of years of water erosion. And not only this, but that at some time in its history this great valley has been partly filled, forming on one or both sides of the river level areas, called bottom land. These lands are exceedingly productive, owing to the great depth and richness of the soil. For many years the writer lived upon one of the river's tributaries to the Ohio, and often made trips by steamboat up and down the Ohio River. Traveling along this river, a close observer will be struck by the exactness of the stratifications in the rock and in the coal beds to be seen on each side of the river. They match as perfectly as the grain of a block of wood when sawn asunder, showing that these coal beds were formed at an age long before the water cut this sinuous groove. What the water was doing while these coal beds were forming will be brought out in some future chapter. All the rivers that are tributary to the Ohio, such as the Monongahela, the Allegheny, the Muskingum, the Tennessee, the Cumberland, the Kentucky, the Wabash, the Miami, the Licking, the Scioto, the Big Sandy, the Kanawha, the Hocking, and the Great Beaver, besides numerous smaller streams, have their own valleys that have been worn away by the same process, and to a greater depth than they now appear to be. All of the material that once filled these valleys has been carried down by the water filling up the bottom of the ocean and building out the great delta of the lower Mississippi. Mountains have been worn down and carried away by the action of the running water until their height is much lower than in former times. The Great Lakes that were enlarged during the glacial period, and in some cases wholly created, by the scooping out and damming up of the waterways and by piling glacial drift around their shores, have had some of their outlets raised to a higher level, and others have been created anew. The old riverbeds that formerly carried the water that is now drained through the St. Lawrence were eroded by the action of running water to a great depth, as is shown by numerous borings along the valleys of the Mohawk and down the Hudson. The salt wells at Syracuse, New York, have been put down through glacial drifts and the salt waters found in the bed of the old river. Great bodies of salt are found at that low level, constantly dissolved by the water percolating through the sand and gravel of the glacial drift. This salt water is pumped up and evaporated, leaving the salt, forming one of the important industries of that region. All of the rivers from the Ohio eastward tell the same story, which is that at some remote period the land was much higher above the level of the sea than it is today. The bottoms of many of these old riverbeds are lower than sea level, but as they were made by running water, they must have been at one time above that point. There is abundant evidence that the earth sinks in some places and rises in others. Along the ridges of some of the eastern mountains are found in great abundance the products of the bottom of the ocean. These evidences show that at some period, when the mountains were formed, a great convulsion of nature raised the bottom of the ocean to thousands of feet above its level. Evidences of this exist in various parts not only of the United States, but of the world. You ask, if this erosion goes on and the mountains and hills are carried down and filled into the low places of the ocean, what is the final destiny of the earth that now appears above the surface of the ocean? Evidently, if the earth should remain without further upheaval, at some time in the far, far future, the land would gradually wear down and be carried off into the ocean, and the ocean would gradually rise, owing to its restricted area, until it would again cover the whole earth, as it undoubtedly did at one time in the earth's history. This fact need not occasion any uneasiness on the part of those who are living today, or for millions of years to come. The problem of building a world and then tearing it to pieces is a very complicated one. There is a constant battle going on between the powers that build up and those that tear down, and this is as true of character building as it is of world building. The world has never been exactly alike any two successive days from the time its foundations were laid to the present moment. It seems to be a fundamental law of all life and growth, as well as of all decay, that there shall be a constant change. There is no such thing as rest in nature. The smallest molecules and atoms of matter are in constant agitation. In the animal and vegetable world, there is a period of life and growth, and a period of decay and death. And this seems to be the destiny of planets themselves, as well as the things that live and grow upon them. Still, science teaches us that with all this turmoil and change, nothing either of matter or energy is lost, but that it is simply undergoing one eternal round of change. Does this law apply to mind and soul? Do we die, or do we simply change?